All right, so here's how the table method works. I've copied the relevant information about the disease. It's rare, 0.04% of people have it, and the tests are pretty good. If you have it, 99% chance the test comes back positive. If you don't, 2% chance the test comes back positive. So what I'm going to do is I'm going to draw a table that represents a large number of people that I can connect this problem to. And what I'm going to do is I'm going to label the rows of the table to be my event of interest, basically that I have the disease, and its competing alternatives, basically that I don't have the disease. So I'm going to label the rows that I have it or I don't. And then what I'm going to do is I'm going to label some columns for the pieces of information that I'm going to be conditioning my probability calculation on. So in this case, what are the pieces of information I might receive? Well, I could receive that the test comes back positive, or I could receive the news that the test came back negative. So the columns are just going to represent the possible bits of information I could have received in dealing with this probability calculation. The test either could have came back positive or the test could have came back negative. And just like most tables, I'm going to have a column for total. I'm going to have a row for total. And what I like to do to connect it with reality is to work through the numbers for a large number of people. And so in this case, I'm going to think about what happens if I were to apply the test to 10 million individuals here. I'm going to draw a few more lines just to make it easier. All right, so this is going to be our table approach. We're going to label the rows by the event of interest. In this case, I do have the disease versus its competing alternative that I don't. The columns I'm going to label as the bits of information that I could possibly be conditioning on. Either the test comes back positive or it comes back negative. And I'm going to envision a large number of people overall in my little experiment. So 10 million people. One thing I know is that if I split this up into individuals that have it versus don't, okay, all I got to do is multiply that 0.04% by that 10 million to get the number of people that do have it. So if I were going to kind of split these 10 million people into two different groups, only 4,000 would actually have the disease, and the remaining 9,996,000 would not. That's just how rare that disease actually is. And so my goal is to continue to fill in this table here, and then eventually this conditional probability calculation will emerge. Without any additional information on one of these 10 million people, picking one of these at random, there's a 4,000 out of 10 million chance, that 0.04% chance of having it. How does that change when I try to incorporate the fact that the test came back positive? All right, so let's work with the top row here. Let's imagine that we're one of these 4,000 people here that do have the disease. Well, sometimes the test will come back positive, sometimes the test comes back negative. One thing that we know is that if we do have the disease, 99.9% of the time the test comes back positive here. So 99.9% of 4,000 works out to be 3,996. Therefore, the remaining 4 people that have the disease end up with false negatives here. And let me do the same thing for the people that don't have the disease. A little under 10 million there. If they don't have the disease, I know that 2% of the time the test comes back positive. So 2% of 9.996 million works out to be 199,920. And so the remaining people here, the remaining 9,796,084 individuals who don't have the disease end up having their test come back negative. So what are these totals? Well, I can add these two numbers together. Out of these 10 million people, I expect to get just over 203,000 positive results and 9,796,084 negative results. All right, so here's what I mean by that reduction of the sample space. A conditional probability is just a standard probability, just with a different sample space than what we started out with. We started out saying, okay, well, we're one of these 10 million people here. What's the chance we have the disease? 4,000 out of 10 million, that 0.04%. Now we're adding new information into the mix here. The test came back positive, so I know that I'm living inside this column here, the test positive column. How many people are in that test positive column? Well, my new sample space, I know that I'm one of these 203,916 people. So if I randomly pick one of these, what's the probability that that person is going to have the disease? Well, that's going to be that 3,996 divided by 203,916. So the probability that I have it, given that I test positive, is going to be the ratio of these two numbers. I know that one of these 203,916 people, we're selecting one at random, there's 3,996 positive people here. So that's going to be that 3,996 over that 203,916. And so when you go and actually do the math, that works out to be just under 2%, 0.0196. So we started out with a 0.04% chance of having that disease, our prior probability. We threw in additional information into the mix. The test came back positive, and we found that probability has skyrocketed up by a factor of about 50, but we've ended up with still a relatively low probability of having the disease at just under 2%. All right, so let's do the Monty Hall problem now with the table method. And once again, when I draw my table, what I'm going to do is I'm going to label the rows after the event of interest, the probability that I want to be calculating. So let's kind of lay down how this problem is working once again. What I'm going to do without any loss of generality is assume that we always pick door A, just to make the computation straightforward. So Monty Hall is going to go and reveal a goat either behind door B or door C, and he's going to ask us if we want to switch or if we want to stay with door A. So the event that I'm interested in calculating the probability of is that the car is behind door A. So if it still is, then, if I stay, then I win. If I switch, I lose. I want to use this table to explore this optimal strategy. So the event whose probability that I want is that the car is behind A. And the competing alternative, we label the rows by the competing alternatives. I'm just going to say that the goat is behind A. It's either going to be one of the two. So here are my two possibilities. And I'm always going to label the rows over my event that I'm calculating the conditional probability of and its competing alternative or alternatives. And then for the columns, I'm going to break down the bits of possible information that I might receive. So what might happen when Monty goes and reveals something behind another door? Well, maybe he shows us what's behind door A. He never will, because we always pick door A, but I'm going to have that there for completion. He might show what's behind door B, or he might show what's behind door C. And so I'm going to make a column for total. I'm going to make a row for total as well. And just like with the rare disease example, I want to give this a real-world analog, a real-world connection, and envision a large number of games. So what I'm going to do is I'm going to figure out, well, what happens for 300 games of Monty Hall here? All right, so if I'm dealing with 300 games, I know that initially the car is randomly placed behind door A, B, or C. So of those 300 games, the car is going to be behind door A in 100 of them. And the goat's going to be behind door A in, obviously, the remaining 200 of those. Okay, so let's try to fill in the columns here. So we're going to deal first with those 100 games where the car is indeed behind door A. So if that's the case, how many of these 100 games will it be where Monty shows us what's behind door A? Well, 0, because Monty's never actually going to show us what's behind the door that we picked, so we can just put a 0 there. How many of these games will he show us a goat behind door B? How many of those games will he show us a goat behind door C? Well, in this case, if the car is behind door A, he has a choice. He can show us either what's behind door B or door C. Let's just imagine that he chooses randomly. It doesn't really matter either way. So 50 of those games he'll show the goat behind door B, and 50 of those games he'll open up door C to reveal the goat. All right, well, what about those 200 games now where a goat is behind door A? Okay, well, how many of those 200 games will Monty show us what's behind door A? Never. He never shows what's behind the door that we originally picked. And so we have to think about, okay, well, how many of these 200 games will he show us what's behind door B or door C here? So if the goat is behind door A, well, the car is behind either door B or door C. Now, since initially the car is just placed completely at random, and Monty doesn't have a choice at this point over which door he has to show us. If the car is behind door B, he's always going to show us what's behind door C, and vice versa here. That means of these 200 games, he's going to show us what's behind door B 100 of the time, because half the time it's going to be behind door C, and half the time the car is going to be behind door B if we know the goat's behind door A. So of those 200 times where we end up picking a door with a goat behind it, 100 of those times he'll show us behind door B, and 100 times he'll show us what's behind door C here. Okay, so let's compute the following conditional probability. What's the probability that the car is behind A, given that he showed us what's behind door B? Initially, the car is randomly placed behind any one of these 3 doors, so the prior probability is fairly easy, just 100 out of 300 here, a 1/3 shot of us picking the door with the car behind it. Now that we've thrown some additional information into the mix here, he showed us a goat behind one of those doors, specifically door B. Well, it's just a standard probability calculation, now with a different sample space. Here is the sample space that we're living in now, because we know this happened. He showed us what's behind door B. There were a total of 150 games where he revealed a goat behind door B. What's the probability that the car is actually behind door A? Well, that's going to be 50 out of 150. Or there's that 1/3 once again. In other words, if we originally picked door A, the probability that the car is behind door A, given that he showed us a goat behind door B, is only 1/3. That must mean that there's a 2/3 chance of winning if we switch to door C, the one that he hasn't opened. And we would get the same probability working out if we were conditioning on the goat being shown behind door C or any initially picked door that we picked. It's always going to be to our advantage to switch in order to maximize finding that car behind one of the doors. For the last problem that I want to illustrate with the table method, I want to talk about the post office. So the post office has machines that read in what's written on the top of an envelope, and they have a digit recognizer that most of the time does pretty good job at identifying what digits are written. So here's the scenario. We've run an envelope through one of these machines, and the machine claims that the digit of interest is a 3. We would like to know, okay, well, what's the probability, given this information, that the digit actually is a 3? We know the machine claimed it was a 3, so is it really? That's what we aim to find out. Now, here's the information that we know. We know that on envelopes, all digits are equally likely. Not really true, but for the sake of illustration, the prior probability of the digit being a 3 is going to be 10%. 10 digits, 0 through 9, 10% chance any given digit is going to be a 3. And here's some information about how well the recognizer performs. We know that if a digit really is a 3, then the machine claims it's a 3 91% of the time. So it's pretty darn accurate. If instead the machine, or if the digit is an 8, well, the machine is going to claim it's a 3 2% of the time. 3s and 8s kind of look similar here, so it can confuse the machine a little bit. And if the machine, or if the digit is any other digit, 0 through 2, 4, 5, 6, 7, or a 9, it's going to claim that digit as a 3.8% of the time here. So if the digit is a 3, most of the time the machine correctly identifies that. If it's an 8, 2% chance, it's going to be identified as a 3. And if it's some other digit, only a 0.8% chance, it'll be identified as a 3 by that machine. So I'd like to know, machine just said, hey, this digit's a 3. Is it? Is it actually a 3? Let's use the table method. So once again, what I'm going to do is I'm going to draw a table, and I'm going to label the rows over the event that interests us, namely that the digit is actually a 3. So one of these rows will be devoted to the digit actually being a 3. The other rows I'm going to label as the other possibilities of what it might turn out to be. It could be a 0, it could be a 1, it could be a 2, it could be a 3. So I'm going to label these rows that the digit is actually a 0, actually a 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we're interested in if the digit's going to be a 3. The other possibilities that it might actually be, that's what we always label all the rows. The event of interest and its alternatives. And then for the columns, what we're going to do is fill in the ways that we could have received that additional information, what we're conditioning on. Here we know that the machine claimed that it was a 3, but it could have claimed that it was something other than a 3 here. So we could say it claimed that it was a 0, just for completion here. Claim that it was a 1, 2, 3, 4, 5, 6, 7, 8, 9. This looks like it's going to be a really big table, but it's going to simplify actually to our delight. So we're going to have a total and a total down here as well. And so to connect the calculation with the real world, let's imagine what happens for a total of 10,000 different digits that this machine is going to try to recognize. All right, so here is what all of our tables are going to start out with looking like. On the rows is going to be our event of interest, the event that we're calculating the probability of, actually a 3, versus its competing alternatives. It's actually a 0, 1, 2, something else. The columns here are going to be labeled on all the different bits of information we could have conditioned on. In this case, it's claiming that the digit is a 3, but the machine could have claimed that it was one of these other digits as well. So first thing we'll do is we're going to fill in the row totals. If we're dealing with 10,000 digits, we know that all digits are equally likely to appear. So of these 10,000 digits, we expect 1,000 to be 0s, 1,000 to be 1s, 1,000 to be 2s, 1,000 to be 3s, etc., etc., etc. All these rows are going to be 1,000. Okay, Well, let's fill in the column after what actually happened here. Let's fill in the column for the machine claimed that it was a 3. So of those 1,000 times that in actuality the digit was a 0, how many of those times will the machine claim that it's a 3? Well, we know that when the digit is something other than a 3 or an 8, there's a 0.8% chance that the machine is going to classify it as a 3. So 0.8% of these 1,000 instances, or 8 times, it's going to claim it's a 3. And if it's actually a 1, well, same sort of deal. 0.8% of the time, it's going to be claimed to be a 3. Same thing for 2. If it actually is a 3 here, I draw some little lines to kind of represent what numbers I'm matching up with. If it actually is a 3, the machine gets it right 91% of the time. So of those 1,000 times that it actually is a 3, it's going to claim it's a 3 910 times. A 4, a 5, a 6, a 7, 0.8% chance, 0.8% of those 1,000 instances, it's going to get called a 3. And same thing for 9 here. 8's the only thing that differed from the other digits here. When the actual digit is an 8, the machine claims it's a 3 2% of the time. So of these 1,000 times the machine is actually working on the digit 8, it's going to claim that it's a 3 2% of them, or 20. So if we add up this column, what do we end up getting? So doing it in your head or cheating and looking at the next slide, we find that there's going to be 994 instances where this machine says, hey, I'm dealing with a 3 here. So here's that reduction of the sample space. Here's the sample space changing. Originally, the prior probability that we're dealing with a 3 is 10%. If we imagine 10,000 different digits, they're all equally likely. Well, 1,000 of those are going to correspond to 3s. So we started out with a sample space of essentially size 10,000. Now we're conditioning on a piece of information that the machine claims this is a 3. That's changing our sample space, and now we're actually living in one of these 994 instances. There's 994 cases where the machine is going to claim that it's a 3. What's the probability that it's actually going to be a 3? Well, 910 out of those 994 times, it's going to end up being a 3 here. So we get a 910 divided by the 994. And so this works out to be 91.55%. So a little bit different maybe than what your intuition would have suggested. I think most of our intuition says, oh, well, if a digit's a 3, the machine's going to claim it's a 3 91% of the time. So most of us feel that it's correct in saying, okay, if the machine claims it's a 3, it's actually going to be 3 91% of the time as well. And in this case, the answer comes out to be, pretty darn close. There's not too much of a difference between maybe what our intuition suggested and what the actual answer was. But it just goes to show you that it's always good to go through the math. And as long as you think of it in terms of, okay, whenever we condition a probability, condition some sort of event happening, it's just calculating a probability with some new sample space that's hard for us to wrap our head around. We can get to that sample space writing out these tables. We can get to the sample space kind of going through the math as well, which we'll introduce in a second. Then it's really not that bad of a calculation. So to summarize what the table method is all about, it is just a way for us to more fully understand what that new sample space is after we condition on events. So it's still a standard probability calculation, just with a different sample space. That table, I think, really hits it home. We just got to make sure that we can set up that table correctly. And so here are my tricks for setting up that table and getting it right every time. So number one, once I've drawn that table, what I'm going to do is I'm going to label the rows after the event of interest. So I want to know what's the probability that it actually is a 3, given the machine claimed it was a 3. I want to know the probability I have the disease, given the test comes back positive. Well, I'm going to label the rows have disease versus not have disease, or actual 3 versus actual 0, 1, 2, etc. So you'll label the rows after the event of interest and its competing alternatives. Sometimes it's okay to just lump it into A and not A. And then what you'll do is you'll go and label the columns based on what you're using in the conditioning. And you'll list all the different ways that information could have turned out. So the test came back positive, or the test came back negative, or the machine claimed it was a 0, or a 1, or a 2, or a 3, or 4, or 5, or 6, or 7, or 8, or 9. Sometimes it's okay to lump that into what the specific information that you are conditioning in your calculation versus not that. So you'd only have 2 columns here. And then what you want to do is you want to envision a large enough number of individuals or a large enough number of trials so that your numbers inside the table work out to be nice and integers. So as long as it's big enough, you'll be fine. But even if you come out with fractions and decimals, that's still okay. So what are the next steps? Well, what you do is you go and calculate the row totals using the prior probabilities of each one of those events. The prior probability of having the disease, the prior probability of not having the disease, the prior probability of a 0, 1, 2, 3, etc. And those are always given to you by the problem. So you can immediately fill in what those row totals are. And then what you can do is fill in the column totals. And in fact, you only need to fill in the column total or the column entries for that one column that's representing the piece of information that you are using to condition on here. So you really only need to fill in one sort of column here, and then the answer is just a simple ratio. That column and how it's broken down gives you your new sample space, and then you simply count up the number of entries in that row for the event of interest, divide by that column total, and you have your conditional probability.